Okay, so Manish, you can start.
Okay. Okay. So can you hear me?
Yes, loud and clear.
Yeah. So thank you, Pansa. So good morning to one and all present here. I thank Professor Pant and the concerned faculties and officials at Plaksha University for giving me this opportunity. I am right now speaking on behalf of the LTA Systems Laboratory. Uh, as already introduced earlier, I am basically a postdoc currently working as an postdoc assistant professor in the Silesian University of Technology in Poland. I was basically associated with the LTA Systems Lab from the year 2021 to 2024, wherein I was part of a number of research and development engagements related to LTA systems. Based on that experience, I am here to deliver a particular talk on the topic of aerodynamic analysis of airships, a way towards bringing back sustainability in the skies. So, the particular lab that we basically represent, the LTA Systems Lab, has been engaged in research and development of lighter than air systems from more than 2 decades. In fact, we are the pioneering lab that works on this field in the whole of Asia. The images that you see in this particular slide are basically the airships that were developed in house by the various R&D teams of of this lab. So we have been privileged to have been able to pioneer this technology on a national level in India. So, considering the fact that these systems are very low speed in nature, people don't realize how a low speed nature can be a very complex problem to solve. Lighter than air systems, we generally say, are a complex flow carrier. That is why aerodynamic analysis related to these applications are paramount, and hence the particular talk that you are a part of. This is an outline of my presentation today. I will be basically, since this is the first lecture of the series of guest lectures, I will be briefly giving an introduction on the LTA systems, brief history of the airship technology evolution. Then we will move on to the main topic of our today's talk, that is the aerodynamics of airships. What are the different methods to understand the overall aerodynamics of airships, and the most appropriate method that has been used recently is the CFD analysis, and I will be covering in that in a later section. After that, I will also cover certain CFD investigations that we at IIT Bombay had carried out previously to understand the aerodynamics related to airships, and then finally concluding with the concluding remarks. So, in just because this is part of the LTA's Delta's course that has already been started by Professor Pant at Plaksha University. I don't need to get much into detail about introducing. So these are basically systems that generate the overall lift by measure of aerostatic lift. So this aerostatic lift is governed by the famous Archimedes principle. The Archimedes principle states that whenever there is a low density body suspended in a higher density body, an upward force is generated on that, and that force is called the buoyancy force. In the case of lighter than air systems like airships and aerostats, we make use of hydrogen or helium filled inside an envelope that produces the required density difference, and hence the buoyancy force. Lighter than air system. This is a brief comparison of lighter than air system versus heavier than air systems. So I'm pretty sure Professor Pant has already covered most part of it. However, for our current lecture, the most notable point to be considered is that these are basically based on producing lighter than air systems are basically reliant on the aerostatic lift and a subtle amount of dynamic lift, whereas heavier than air systems, they do not generate any aerostatic lift. They are basically solely dependent on the lift generated by the propulsion systems that are fixed on the systems. Because of these, lighter than air systems are more fuel efficient. They operate on they make use of less operating mechanisms. However, because of their overall blunt geometry, they are very slow and highly susceptible to weather conditions. So the most notable point about these is that they are highly fuel efficient. That is the sole crux of why these systems are again coming back, despite the heavier than air systems being faster and more robust with respect to weather. So there are three types of LTA systems. One is the aerostat. These are basically static in nature. They are unpowered. They include only stabilizing surfaces to provide stability to the device. These are basically static at a particular altitude and a particular position to carry out a particular application. The second and the most notable form of LTA system is called the airship. These are maneuverable. Basically, they are fitted with certain propellers and thrusters to carry out the maneuvers from one place to another, and hence they are provided directional control. The third, and most of the students might know, are called the hot air balloons. These are basically filled with hot air, and based on the buoyancy of the hot air, the particular payload is lifted up to a particular altitude. In the present talk, we'll be mainly focusing on the airships. So before going on to the more intrinsic details, we should firstly cover the fundamentals. So what are the principles? Whenever an airship is suspended is operated, there are four forces that act like any other aerospace application. Thrust that gets applied in the forward direction, drag, which is opposing this forward motion in the opposite direction of the motion, weight because of the mass of the body, and the lift that is generated because of the overall aerodynamic and aerostatic lift. So the most amount of lift related to airships is generated because of the Archimedes principle, and as I mentioned to you, this is based on the difference between the outside air and the gas that is engulfing the envelope. So based on this difference, we generate the required amount of lift, and we can take a particular application on board at a particular altitude and do our particular application. That might be any scientific observation or a leisure flight or anything. So these are the two components: the gondola that houses the payload specific to that airship application. That can be any sensor, a telemetry sensor, or any particular sensor. In the case of a cargo transport, that could be a housing related to housing the basic payload. Then the second important aerodynamic surface is the control surfaces. These provide the required stability as well as controllability to the airship to maneuver it from one place to the other place. The third and the most important part of airships from an aerodynamic standpoint is the envelope, because envelope is the most contributing component related to different aerodynamic aspects related to airships. So based on the overall structure, there are different types of airships. First is called the rigid airship. So the way these are basically categorized is that the outer shape that you see, which particular component maintains that shape determines the overall airship type. So in the rigid airship type, the shape that you see outside is basically maintained by the rigid body. This rigid body is embedded with a number of gas bags, which have the lighter than air gas. Based on these lighter than air gas, the overall buoyancy force is generated. Second type is called the non-rigid ships. These are also called the pressure ships or the dirigibles. So in these particular types, the shape is maintained by the envelope itself, and the payload that you see in the downward direction, that is suspended via curtain to the envelope. The third and the most notable ones which are being used very profusely these days is called the semi-rigid. Basically, here the shape is maintained by the envelope, but there are certain reinforcements that are installed, that is able to through which we are able to install other supplementary controls like the propulsion systems or the payload and the control surfaces. So and the fourth one, that is the hot air airship, wherein we make use of the hot air to create the required buoyancy and hence take it to the particular destination. The fifth and the most progressive type of airship is called the hybrid airships, wherein rather than making use of only the aerostatic lift to generate the lift, we may also make use of the dynamic or the aerodynamic lift to generate the lift. Because of the combination of these two lifts, we are able to generate a lot of lift, and we can carry a lot of payload without causing a lot of fuel consumption. So then based on these, let's have a look at the historical. So as a researcher, I always suggest all the students that whenever you want to actually draw interest towards a particular topic, you should have a lot of focus on the airships. Perhaps this is why I was so much interested in the airships. So from my understanding, the airship evolution can be divided into these five parts. In fact, airships can be very easily touted as the technology of the first. Or most of the aeronautical technological development that we see, those would not have happened if there were no airships developed. So in the 18th century, the Montgolfier brothers, as many of you might know, they developed their first hot air balloon, and this was the first flight wherein a man was able to ascend to a particular altitude. Then in the 19th century, you see this Santos Dumont airship. He developed a series of airships. Most notably, you can see that the design of the airship has now come from a spherical design to a more streamlined design. So airships can be touted as a way of how aerodynamics also evolved in the aerospace industry. So then in the 20th century, considering how these could be operated this could be operated with very little fuel consumption and could operate in a very stable fashion. These were used comprehensively by the Germans during the World War I era. These airships, through airships we were able to obtain the first transoceanic flight from Germany to USA. Considering these advantages, these were comprehensively used in World War I by German military. Subsequently, in World War II, the US also made use of these airships for submarine patrolling missions. Subsequently, after post-World War, what happened? There were a series of incidents, and also the heavier than air systems had come into the picture. Because of that, the application got limited to only mostly the tourism and advertisement. So, however, in the last 2 decades, considering the increased cost price, considering the development in material and safety technologies, many companies are now coming on board, and many countries are are also trying to come into in this particular field, and now these are being touted to be used for not only for cargo advertisement or tourism, but now they are also being used for explored for cargo as well as space exploration missions. So word on here, airships cannot be taken
Manish,
without.
Manish, sorry, may I interrupt? Maybe you skip Hindenburg. They have done a detailed
Okay.
assignment on that. Just go ahead.
Yeah.
Come to aerodynamics.
Yeah, so these are certain applications. So because of their level, because of their stability and their long endurance, these are being used for various applications now. And now many more companies are coming that will be using them as electric airships, stratospheric airships, cargo transportation, and luxury flights. Moreover, space applications are also being explored through the usage of airships. So these are some of the airships are USPs of airships are that they can be operated from open fields. They have a large cabin space, low noise, low environment pollution, and many other benefits. So that is the whole reason why there has been a recent surge in their application. In fact, these fall in the best position, optimum position from a transportation point, wherein they provide you a faster speed as well as lower fuel economy. That is why there is a lot of surge in the overall LTA research avenue. Because of this, there a lot of R&D is being carried out overall. This R&D can be categorized in mainly three categories: aerodynamics, fabrication, and structural concerns. In our talk, we will be focusing mainly on the aerodynamics. So what is aerodynamics? If I want to understand what is aerodynamics, basically whenever the airship is operated in a surrounding air, the flow will move upwards and lower and below the surface. Because of the interaction between the air molecules and the solid body, there will be interactions. So aerodynamics is basically the study of the properties of moving air and the interaction between the air and the solid bodies to moving through it. So based on this understanding, we calculate the different flow variables, that is the pressure and velocity, through which we can understand the different performance metrics related to airships, and through which we can understand the overall performance of airships. So this is what aerodynamic study is. Because we are considering airships which operate mostly in low subsonic applications, the most important parameters that an aerodynamic analysis entertains are the velocity and pressure distribution. So keep this in mind. I will be asking a question regarding this in the future in a particular slide. So the aerodynamics can be further categorized into four parts. First, how the lift is generated, what are the lateral forces, what are the drag penalties, and what are the pitch and yaw momenta. Let's understand these different components separately. So whenever an airship gets exposed to external flow, these aerodynamic forces are generated. These are categorized as lateral forces. So these lateral forces come into picture because of the presence of side wind conditions. The pitch yaw momenta comes because there is always a tendency of the airship or any airspace application to to rotate about a particular axis, and this is where the pitch and yaw momenta understanding comes into the picture. The lift is one of the most important aerodynamic parameter related to airships, because in the modern airship designs, these are not only limited to aerodynamic and buoyant lift, but also to vector thrust lift. So this is also one more. So the overall lift that is generated by the airship through these components will ultimately determine what is the payload carrying capacity of your airship. So as you this lift will ultimately determine how much payload you can carry. This will be a sum of buoyancy as well as aerodynamic lift. So as you go on increasing the envelope, your lift also increases. But on the contrary, the drag penalty also reduces. Now, what is drag? Drag is basically opposing the motion of these airships, and hence will determine the overall performance of airships, overall efficiency of your airships. And hence there has been a lot of study that is taken in the past to address this shortcoming, and how to mitigate this problem. So let's understand this drag. In the case of airships, this drag is basically composed of two components. First component is the viscosity induced skin friction drag. The second is related to adverse pressure gradient and induced drag. The drag that is associated with these is mostly because of the presence of the airship hull. So let's understand these drag components first. The first component that I mentioned to you was the viscous drag. So now what happens whenever an aerospace application is subjected to free stream flow, these particles try to that impinge on the surface, they try to they try to stick onto the surface, and that leads to the reduction of momentum, and hence there is a inherent resistance to the airship that is provided by the flow. This is called the viscous drag component. The second component that opposes this motion is called the pressure drag component. Now this originates because of two subcategories. First is called the adverse pressure gradient, and second is because of the blunt surface. So in the first case, for example, when you see this body and there is an incoming flow at the initial phase, the flow is able to traverse the surface without any problem. However, as it approaches towards the converging section, there is a inherent opposition to this flow. The flow's velocity tends to reduce, and hence at a particular point B in this particular image that you see, this is called the separation point. So after this, the flow is no longer able to follow the actual flow velocity, and it goes in a reverse direction. This is called the flow separation region, and because of the presence of these flow separation regions, there are a lot of eddies and backflow phenomena, which is basically the responsible for the pressure drag. On the other hand, when we talk about any airships are very blunt in nature, and because of that there is also a pressure. Let's understand this. So whenever a blunt surface is subjected to an incoming flow, because of the bluntness, there is a pressure differential between the front and the rear end. Because of this, there is a suction region that you see in this figure is generated behind the airspace. This is responsible for a lot of eddies, and hence the pressure drag. However, if we basically streamline the flow, there is an additional disadvantage that the wetted area increases and hence the viscous drag increases. So whenever we are trying to optimize our geometry based on these two components, we have to strike a balance between how much viscous drag we can cater to and how much pressure drag we can reduce. So there is an optimization that is involved in mitigating this. The third component, because these airships are three-dimensional in their geometry, there is an inherent three-dimensionality related to the flow. Because of this particular flow characteristic, there is a lot of induced drag that is generated. I will not be covering much into this because of the brevity constraints. Then the fourth is called the interference drag. So at the interjection between the airship and the fin body, there is flow interference between the two boundary layers. This leads to the generation of interference effects or the interference drag penalty. So let's address certain complexities now. We went through the basics now and understand because of these because of the high Reynolds number and low Mach number condition, there are a lot of flow complexities involved in airship aerodynamics. First, feature transitions. Because your flow is very low Mach number, any amount of protrusion in the airship will lead to a lot of transition, and that leads to flow complexity. The second is because of the overall blunt geometry, there is a wake formation at the stern portion. This leads to the generation of a lot of non-linearities in the flow, and hence the flow becomes complex. Additionally, because of the low subsonic and the high Reynolds number characteristic, there is a lot of interference between the hull and the fin surfaces. As you can see in this particular paper, there are not only primary but also secondary type of smaller shape, smaller size. It is that generate from the airships that lead to flow complexities. Now, as I already mentioned, the flow is three-dimensional in nature, and that leads to the generation of vorticil flow. Boundary layer airships are also amenable to a lot of boundary layer separation because of the adverse pressure gradient that I just mentioned to you. In fact, this is one of the most important factor that needs to be understood while carrying out aerodynamic analysis of airships from the scratch. Then because of the high Reynolds number, there is a tendency of the flow to transition from laminar to turbulent flow, and hence the lead to generation of a lot of eddies and vortices that leads to further flow complexities. Now, unlike normal conventional wings that generate the lift, airships are airships generate lift in a more non-linear fashion, and hence a proper care has to be taken throughout the angle of attack operations to understand the overall aerodynamic performance. This is the most recent form of airship complexity that has been investigated. So added mass phenomena. So because of the big size of the airship, these are linked with a lot of added mass phenomena. So this is similar to what your car would feel when it is trying to start. So whenever an airship tries to accelerate, there is a tendency of the airship to feel heavier than usual. This is what is called the added mass phenomena. So a lot of study is being done to understand this particular phenomena. So we can very clearly see that the airships are a body of complex flow phenomena, and a lot of study is being taking place to understand the aerodynamic study, to understand the aerodynamics. So why, you might say, that why we need to do the aerodynamics? See, we have the designing tools, we have the optimization tools. Why we need to understand the aerodynamics? So this can be understood from 2 or 3 examples that I just mentioned here. This is one particular study that was carried out in 1969. So they carried out an experimental study on a particular airship embodiment, and based on this understanding, this analysis, they were able to understand that if they are able to incorporate a propeller at the stern portion, they will be able to reduce the drag by more than 40%. In fact, based on this understanding, Goodyear implemented this same technology in their NT models, and they are being comprehensively used in their recent airship bodies. Based on this understanding, we can also understand how the fins and appendages could be placed on the aerodynamic body to improve the overall aerodynamic performance. We can understand how we can design these additional lifting surfaces to improve the aerodynamic performance, and also based on the aerodynamic requirements that we have. For example, in the study that you see, this was carried out by our lab, wherein we try to understand whether a single lobe or a tri-lobe is better for our application. So such a study can be possible only if you start your study by carrying out aerodynamic analysis of the overall geometries. So there are 3 methods to understand the aerodynamics. Firstly, and the most notable ones, most of you might already know, the experimental techniques. During the inception era of this technology, most of the investigations were carried out using this methodology only, that made use of flight test and experimental techniques. So basically this method involves scaling down the particular model and carrying out the overall flow experiments. These experiments are further associated with boundary layer analysis, pressure coefficient distribution, and for aerodynamic force availability. And based on these understanding, we a lot of study these analysis. A lot of paper has already been published in the era 1920s to 1960s. However, it has only been in the recent 10 to 20 years that more papers are coming out because of the popularity they are getting owing to their reduced fuel consumption advantages. So, however, we are though we are able to get sufficient understanding related to aerodynamics of airships through this analysis, but they come with a lot of disadvantages. So setting up aerodynamics, experimental aerodynamics for airships especially is very difficult, and they are also prone to a lot of inaccuracies due to instrument and limitations of the instruments. So the second method that we can make use of is the analytical methods. So what are analytical methods? These are basically semi-empirical relations that that link the flow conditions with the output CL and CD data, that is the force data, based on the experimental data that we have already obtained. So this is a function of the wind tunnel data that we already have. So based on this, we derive a relation and hence form out certain semi-empirical relations to understand the aerodynamics. So there are many very basic type of methods that are used erstwhile. The potential fuel flow theory, wherein we divide the whole body into a number of panels, and on these specific panels we solve a number of semi-empirical relations to understand the aerodynamic forces that are being acted on the airships. So these potential flow theory is very simplistic in nature because they assume the flow to be incompressible and irrotational. They are applicable for only small angle of attacks. They neglect viscosity, and they also lack a universal model. So a particular panel method that you devise will be only applicable for that particular airship body or application that you are analyzing. So there is a complete lack of universal acceptance. So there is an advanced version of this model wherein we integrate boundary layer equations with the panel method to understand the viscosity also with respect to airship, but these are also very simplistic in nature. Then there are certain analytical methods to understand the hidden mass estimation. This is a more advanced version, which is not very appropriate for this particular forum right now. So very recently, one of the speakers that we were able to interact with during one of our conferences at IIT Bombay, a speaker called Jesus Gonzalo, he has developed an airship panel method which is dedicated to airships, and he was able to obtain acceptable level of accuracy through this method, wherein through this method he was able to understand the aerodynamics related to airships. These results are simpler to obtain, but they ensue a number of assumptions. So experimental results are good, but they are expensive to obtain. Analytical methods are easier to obtain, but they are not very realistic from an application standpoint. So now where should we go? So that is why most of the studies that you see these days in most of the aerospace applications, including LTA systems, are making use of the third method, that is the CFD based aerodynamic analysis of LTA systems. So what are CFD methods? CFD methods are basically making use of computational fluid dynamic methods, or in a nutshell, computational tools to get deeper insights into the underlying flow physics. So so through these tools, we are able to visualize the flow across the airship body, and by analyzing these flow parameters, we are able to understand the overall aerodynamics of LTA systems. So let's understand the CFD process
What is
in
this?
a more detailed manner. So how a CFD process
You cover this?
works is like, it makes use of a suite of softwares to design, to analyze, and to process your results to understand the overall aerodynamics. In the first stage, we make use of a model generation software. This could be any software like CATIA, SolidWorks, or any other designing software. This model is further fed onto a different modeling software, wherein we design the flow setup. So flow setup is uh, analogous to setting up the stage for a particular stage performance. So just like in a stage performance, you have to say where a particular performer will sit, what will be the different props that will be using. Just analogous to that, in any CFD methods, you have to tell the solver that what are the parameters that will be that are initially available to carry out the simulation. This is how the flow setup and boundary condition selection happens. In the third phase, the meshing process is initiated, wherein the domain that you see there, that is divided into a number of cells, and it is on these cells that the solver does some calculation and gives you the particular flow parameter values. After all these things are done, after the meshing is done, these boundary conditions and the mesh is fed to the solver. This solver could be anything like OpenFOAM, ANSYS, or CFD++. There are a lot of internal settings that can be selected based on your problem. You can refer to any of the papers that we have published to get more details into that. However, in most of our cases, we made use of the RANS based methods to carry out our simulations. Then after setting up the solver will carry out the simulations. These simulations are further fed onto a post-processing software. These software could be anything like ParaView, MATLAB, TechPlot. Through these softwares, you can carry out this post-processing or the data analysis of these results. And after analyzing these results through your post-processing step, you are able to understand the aerodynamics. This aerodynamics could be in the form of understanding the plots, the flow field visualization plots, or anything. So this is the overall picture of how a CFD process works. Now let's understand the science. What happens actually behind these switches? So what happens is that the air that is surrounding the airship that we are trying to simulate is divided into a finite number of cells. Now this step, as I already mentioned to you, is called the meshing step. I have elaborated this very clearly in this because from airship CFD aerodynamic point of view, meshing is one of the most critical step. If your mesh is not good, your results will never be accurate. So we replace the computational fluid domain with finite cells. Then after obtaining these cells, we need to solve a set of equations. Now these equations from a continuum point of view is making use of something called the Navier-Stokes equations. You can go into the details. These are set of 5 equations, the energy equations, 3 momentum equations, 1 continuity equations. These are very complex in nature. I will not delve into the overall numerical part of it, but you need to understand these are very complex in nature, so, and are very difficult to solve. So in most of the CFD for softwares that you use, we do not make use of these equations, but we actually simplify them. So the most notable simplified versions are called the Reynolds average Navier-Stokes equation, or very lamely called as the RANS equations. So what these do is, basically the Navier-Stokes equations are averaged in the time duration, and these averaged equations are further fed onto the into the solver setup. So because of this averaging, there are some additional terms that are introduced in the equations. To solve those additional terms, we incorporate turbulence models. So you can refer to any of our papers. I have very clearly mentioned elaborated on those particular details related to a turbulence model. But to understand in a very simplistic manner, turbulence model is the way how we achieve the steady state simulations in A-shape aerodynamic analysis. So after setting up all these conditions, we run the solver. Now the solver will solve these equations and get the results of the flow parameters at different points, and that those are subsequently analyzed by your post-processing software. So how these so we understood the physics, the science, how they compare, because the CFD tool comes with a lot of other tools like that are through which we are able to carry out post processing. We are able to understand physics in a more clear manner. We are able to understand the flow physics in a more clear fashion. We can carry out this method across any flow condition that you actually want to operate on, whether it be low high altitude application or stratospheric application, which is not in the case possible in the case of experimental evaluations. With a suitable model and setup, we can also include turbulent flow conditions, which are limited, which are limited in experimental evaluations. One of the biggest advantage related to CFD methodology is that if we want to modify our current state of art, we can modify it very easily through the computational tools. We can analyze it. We do not need to design the costly modified variant and do a experimental setup on the prototype, and hence this methodology is way cheaper from a time as well as budget constraint. But the biggest disadvantage is that they require a lot of computational power and time. So unlike experimental evaluation, wherein you can obtain the results within a minute, within a minute, computational CFD analysis will require some hours, in some cases some days also. So the complexity of obtaining the required solution also becomes more and more complex. So as you go on increasing the number of surfaces on the supplement surfaces on the body, the complexity becomes even more and more. But considering all these things, we think because these come with a lot of post-processing tools, qualitative analysis of these of A-shapes through CFD is the way forward for aerodynamic analysis. So that's why most of the study that has been carried out in our lab has been focused on CFD analysis only. There are certain challenges related to A-shapes. These are very complex in nature, but the most notable points that you need to consider at this stage are that whenever we are trying to carry out CFD analysis, we have to be very sensitive to three different aspects. A, turbulence model, CFD model is very sensitive to the turbulence model you select. B, the mesh that you select is will be very crucial to carry out the aerodynamic analysis. And C, your mesh, your solver, your solver setup will determine how well your solver will be able to capture the boundary layer variations, which is very important to understand the aerodynamics related to airships. So these are some of the critical points that you need to understand before carrying out CFD analysis. So based on this, I'll just mention you some analysis that we have already carried out at IIT Bombay. We have made use of open source software, that is OpenFOAM, to carry out the CFD analysis. This was carried out for single load airships at different angle of attack. We carry out the same analysis for airships with fins also, fin configurations also, and also for different airship embodiments. We also carried out analysis for multi-load airships, and we also carried out optimization study of tri-load airship envelopes. So we have been thoroughly involved in this particular field, and we also realized that our aerodynamic pursuit cannot progress without including the most recent advancement in technology, that is integration of active learning with the CFD methodology. So very recently we have worked on integration of CFD and active learning techniques for design optimization of airships, wherein we made use of OpenFOAM and Python coding to formulate our design optimization scheme through active learning technique. And through this, as you can see this in this particular figure, we were able to obtain a drag reduction of around 3% through this methodology. The paper has already been published. If anybody is interested, they can contact Professor Pant to get hands-on about that paper. Apart from this, we have also done data-driven drag mitigation of trilobe airships. So, for example, in this case, we were through our analysis, we designed a webbed airship design. Because of this the design modification, we were able to achieve a significant 11% reduction in increase in the reduction in the drag value, and hence aerodynamic analysis was able to obtain productive results. So we can say that yes, aerodynamic analysis will play a very critical role in the evolution of airship technology, and hence all the tools that I just mentioned to you, you need to study these tools elaborately. These will not only help you in airship, but whatever aerospace application that you want to analyze in the future. So I just to make the students more aware, much more familiar with the overall aerodynamic analysis of airships, I'll just give you a brief case study that we did. So this is a study related to Zeoan airship that we carried out using the Zeoan airship. This was carried out on the OpenFOAM software. I mentioned mentioned this case study specifically because we carried out it on OpenFOAM. So if anybody of you is interested in carrying out a similar study, the required tools are already available online free of cost. You can go Google and obtain this software and also carry out the same study by yourself. So let's understand this stuff. Before carrying out the study, always a student should understand the problem. To understand the problem, first they should understand what is the model that they are trying to simulate. So this is just a brief detail about this Zeoan airship. These were developed by the China-based company in 2009, and these were basically meant to operate remotely using fuel cells. The overall application was application of this airships was to carry out structural design and propulsion system of airships, and also to understand the overall aerodynamics of airship and fin configuration. So this was the model that we have that this particular study took care of. So whenever we do the literature survey, we will also get the details related to this model. So in this particular case, these are the set of equations that we were able to obtain, and these equations are fed onto your modeling software. After that modeling software is fed with this system, we are able to obtain the contour of the geometry, which can be further processed to obtain the three-dimensional model. So whenever we start our simulation, we should be familiar with the flow conditions that we are going to simulate. So the flow conditions that you see in this was based on a paper that we referred to understand the flow conditions. So first we understood the model, second we understood the flow. Then after understanding these two parameters, we have to do the most critical phase, that is the meshing of the software, meshing of the model. So as I already mentioned to you, this the flow surrounding the model is divided into smaller cells. Now if we go into more detail of the meshing software, because of the over because as we approach the model, the flow complexity becomes even and more. Hence, to capture these flow gradients more elaborately, we have to refine the mesh more and more closer to the cells. Hence you see the zone refinement from zone 1 to zone 3, and hence the number of cells or the mesh refinement is more as we go closer to the model. Based on also, because we are dealing with low subsonic applications wherein boundary layer variations play a very critical role. So there is a specific category of meshing which we called as the inflation layer meshing, that has to be taken care of for every particular A-shape CFD analysis. So whenever you try to understand the meshing, you should always understand what is inflation layer and what is the setting. In our current setting that in the current study that we did inflation based on such that we were able to obtain the results up to up to the very finest level of boundary layer, that is y plus around less than 1. So this stage of ours for CFD analysis plays a very important role in any aerodynamic analysis. So I highly recommend all the listeners, all the students to understand this meshing process, especially for low speed applications like airships. Then after all these things are done, we give the information to the solver as to what is the boundary conditions, what are the inlet and outlet boundary conditions, what are the wall boundary conditions, and subsequently we feed these to the solver that we are using. In this particular case, we made use of the open form solver. So as you see in this method, we made use of the RANS based methods. Then the model that we used, they were SST, K omega, and SA. In a way, there are like more than 5 or 6 types of turbulence model. Out of the lot, we made use of these two methods. In order to understand how these models work, you can refer to our papers. We have clearly mentioned to you. However, we selected SST K omega model because we were able to understand the boundary layer variations more efficiently. So after all these things, the solver will we initiate the solver. It will carry out a sequence of simulations, and hence we obtain the results. Now in any CFD method, obtaining a colorful plot is not the only prerogative. We also need to verify that the results that we get are accurate. To ascertain this accuracy, there are 2 stages to it. First, mesh independence, and second, solver validation. So these 2 parameters have to be carried out in any CFD analysis to ascertain the accuracy of your results. So in this case that you see, we basically had to firstly understand how the different models work, and hence, as you can see in this particular plot, SST K omega was found to be better, and hence we selected that particular model. So this similar study you also have to carry out, and based on this understanding only you select your turbulence model. As I already mentioned to you in one of the slides, turbulence model selection is very critical to your CFD analysis. Second and one of the most important is called the mesh independence. So what we do in this stage is that we increase the refinement of the mesh, that is, we increase the number of cells in stage-wise fashion, and see whether the results are varying from one refinement level to the other. So for example, in this stage, you see from mesh 1 to mesh 2 through mesh 3, the variation is less than 1%, and hence we can say that yes, the results that we are obtaining are independent of the mesh. And they are basically, the variations that you see, they are basically related to the physics. So the most important step after mesh independence is the solver validation. So in this case, what you do is you take a similar model that has already been experimentally evaluated, and we in our solver we carry out CFD simulations for that particular model. We compare our results with the 6 experimental results and see whether they match. If the two results match, then we can say that our solver is validated, and hence based on this understanding we can say from up to an acceptable confidence that yes, the solver that we are using, that can be used for our CFD analysis overall. So this stage of the CFD analysis is very important, and much focus has to be given to this particular stage. So after this is done, we carry out our normal aerodynamic evaluation. We get the different aerodynamic data at different angle of attack. Angle of attack is only one condition. We can vary other parameters like yaw condition or rolling condition, and based on that we can obtain the different aerodynamic results. And based on this we can understand how the overall aerodynamic application like the airship in our case is performing. So as you can see in this particular case of ours, the CL by CD plot, the third plot that you see, this is also called the drag polar plot, by the way. This shows you that the drag polar plot is mostly parabolic in nature, which basically tells that there is an increased level of three-dimensionality involved in the airship's aerodynamics. So after this integrated analysis, we do supplementary analysis that could involve understanding the pressure coefficient distribution plots over the upper and lower surfaces at different angle of attack. And based on this analysis, we are able to understand in more detail the physics that is surrounding the aerodynamics of any airship application. After this, we can also make use of the colorful plot that you always see related to CFD analysis. So as you can see, we are always seeing these CFD color plots and all, but the overall science that goes behind is much more detailed. And if you are able to get tuned with the overall system or involved in any CFD aerodynamic analysis, you will be able to obtain a lot of good results and hence achieve your desired aerodynamic goal. So this is the whole purpose of me particularly covering this particular study. And based on this understanding, I presume that you will be able to get a hands-on of the CFD analysis, and you will be also able to understand how this method works and how it can be of help to you to carry out aerodynamic not only for airships but for any aerospace application in the future. So in conclusion, I will just say that yes, we all know LTA systems are on a rise because of their green aviation characteristic, and in order to progress that in a more productive manner, aerodynamic analysis will be very crucial for its future utilization. Out of all the aerodynamic parameters that are involved, drag is one of the most important parameters, not only for single lobe, tri-lobe, but any other airship embodiment that you want to analyze. This drag is basically composed of two components: skin friction, because of the way flow gets attached to the flow, tries to remain attached to the flow, and pressure drag because of the blunt geometry of the airships. In order to understand the aerodynamics, CFD will play a very critical role in the future, and hence getting acquainted with this particular tool is very important for you to carry out any aerodynamic analysis in the future. Out of all this, I will again re-emphasize that meshing is a very critical step, and whosoever student wants to do an aerodynamic analysis, meshing has to be taken care of very, very critically for your any study. For any prospective advanced who would be interested in any research project, there is a lot of scope in addressing the CFD challenges related to A-shaped aerodynamic analysis, mostly including designing of sophisticated meshing and transition point capturing techniques. So there is a lot of scope in designing tools for aerodynamic analysis of A-shapes overall. So yeah, that's that from my end. I would like to again thank Professor Pant to give me this opportunity, and to all the students, I will just conclude by the fact that yes, teach all my students and all my colleagues that yes, you should never forget the 4 F's of your life: family, friends, faculties, and fundamentals. Fundamentals was the part that I wanted to cover with you today, and I hope I was able to address most of the challenges or confusions related to aerodynamic analysis. And yes, with that, I will say thank you, and I'm open for any questions.
Yeah, you can stop sharing your screen. Yeah, thank you. Sorry for the initial confusion because of the audio-visual system, but eventually we were lucky that we managed to get it working. And also, my laptop is having only about 10% more power. So I 14, 12% power remaining. So,
Okay.
Manish, you have covered in very great detail the do's and don'ts for carrying out CFD analysis for airships. Now, the floor is open now for anyone to ask any questions. If there are any questions, we can take a few questions before we close the discussion.
Manish, very
Yes.
good talk. Thanks.
Yeah, thank you.
My question is not exactly about CFD. What is the Reynolds number like for the airship?
So the Reynolds number can actually vary based on the application of airship. For example, so the airship's size will determine what is the overall Reynolds number. The problem that we investigated that was basically around in a high Reynolds, I think 6 million or so. Most of the airship applications that were used erstwhile, they can be categorized as high Reynolds number, that is turbulent flow characteristic. So, but for smaller applications like indoor airship and applications and all, they can be categorized as a low Reynolds number application. But yes, still the speed, that is the Mach number, will also play a very important role in the overall way you actually design your computational tool.
But essentially, there will be low speed applications.
Yes, they will be mostly low speed applications. So the maximum that our predecessors were able to obtain was I think the Hindenburg. Professor Pant, you can correct me if
Yeah.
my
So, just
I
to
think
give
it
you an
was
idea, the maximum speed of an airship can be considered as about 120 meters, 120 meters per second. Oh, sorry, 120 kilometers per hour.
yeah.
Kilometers per hour. Sorry,
I think
that is
Hindenburg
the
was able to obtain 135 kilometer per hour,
yeah.
but
So
that is the maximum. So yeah.
that is the maximum speed. So the Reynolds number can go up to about 7 to 8 million generally. But the
Application.
lowest in 10 power 5 and about 8 to 10 million will be the highest one.
Are there any experimental studies of the scaled down version?
Yes, so so I have covered only one of them, the Zewan
Any
airship one. That is actually an
guys who are online
experimental
have
one
just
that I've
started
developed.
asking questions. That's why we
There
got
are
in.
some related to the LTA airship variant, which you can very easily come across. That is a paper from
कम हो गया
by
क्या?
one of the scientists in Germany's University of
It was
Stuttgart.
reduced.
What is the scaling down factor?
I think it was 1:13, the scaling, 13 point something, the Lotte issue, from what I recalled. So the scale down model was, I think, if I remember, it was 0.86 meter in length. Yeah, 0.86 meter in length.
And it was tested in air only.
Yes, it was no, it was tested in an experimental setup.
Yeah, I mean the fluid was air.
Yes.
Okay.
I have the paper with me, Shashikant. I can share with you. It was in open jet tunnel in China, so I can share the paper with you. I
Sure.
think, Andy, you have some question, if you can.
You know, if things go well, what's the cost of transport of these airships compared to a slow airplane, a train, a truck? Uh, how much energy does it take for you to wait to distance?
Okay. This question will be answered by another speaker who talks about cargo airships, where he will compare the cost of transporting cargo through ships, trains, and aircraft. So that will be 2 weeks from now, 2 or 3 weeks from now, 2 or 3 weeks from. So every Monday till 5th of May, we are going to have talks like this by people on different topics. So this question will be best answered at that time. Manish is going to focus mainly on the aerodynamics aspect. Anybody else have any question? Yeah, you can speak loudly.
Yeah, so I have a little more.
Are you able to hear, Manish?
Yes,
Why don't
yes,
you
yes.
come here? Just come here. So he has a little bit more fundamental question.
Yeah.
Yeah.
I have a couple, like some questions. First is, I wanted to understand how is the length scale for the Reynolds number in case of airships known? Like, what is the length scale here? So the velocity we know, like, so
So whenever you do scaling down of any particular, not only for airships but for any airspace application, that scaling down is based on two similarity parameters. These similarity parameters
You
are
come
called
here.
the Reynolds number and the Mach number. So, for example, there is an airship that is operating at a particular X speed, for example, 135 kilometers per hour. Okay, that 135 kilometer per hour will have an associated Reynolds number and Mach number value for that.
Manish, I think his question is what is the length scale of the problem?
yeah.
The
Length scale
problem
as in what is the length scale used in the calculation of Reynolds number?
okay, I understood. Yeah, so in general, we make use of a specific term called basically volume to the power 1 by cube.
Okay.
So we take the envelope volume and we cube root it. So that is the reference length, and the surface area reference area will be the square of that value.
Okay.
Yeah, go ahead.
Yeah, go ahead.
So uh, in undergraduate, we kind of make many approximations for friction in many systems. So, is there any approximation for airships? Like, is there
So
some kind of functional approximation?
no, so approximations will be dependent on the methodology that you're using. So CFD methodology also has its own set of assumptions. Analytical method has its own set of simulation assumptions and all. So it all boils down to what methodology you're trying to make use of.
Okay.
Yes,
And
it's similar to any experimental setup, you say, right? So whenever you do any experimental setup, you do certain assumptions. For example, when I'm trying to scale down my model, my A-shape model, I have to assume that yes, we will not be able to capture the same amount of flexibility that is involved. So whenever we do post process our results, we have to do some correction to the obtained results to curtail to this.
okay.
Yes.
Yeah, go ahead. Any other? Manish, can you speak something because we are putting you on some other speaker?
Yes. Hello.
No, it's okay. Any other question anybody has? I'm sorry, actually my laptop power has gone, so I've shifted to my mobile phone. So now the students are surrounding me to hear you. So that's fine. But if there is any other question, we will open it. Otherwise, we'll take a short break because, yes.
So
Come. Huh.
I had like a couple of questions. The lens skill question was answered. Another question that I had was that how is the added mass coefficient like reduced for these airships, because these are not standard shapes, especially for like Yuan and these shapes. Are they empirically reduced, or is there a way to calculating these coefficients for added mass?
So from what I'm not gone much into the details of that, but from what I have read in the literature, at this stage mostly they have made use of analytical methods only. So these analytical methods were derived from those that are previously being used for the conventional aerospace applications only. But since there is an increased amount of the volume of these airships are now increasing day by day, so there is an added there is a tendency that people are considering added mass phenomena also to be a very critical part, and hence a lot of technological new methods are being developed for this particular phenomena. So there is a very good scope for future studies in this particular case.
Anyway, the answer basically is that there are some semi-empirical methods which have been proposed. Most of them are not actually so particular to do with the shape, but more with the volume.
Yes.
So they talk in terms of volume and length more than just shape. So if there are two shapes which are very similar, there will be no difference as per those calculations.
Okay, so like can we approximate to an oblate and like do calculations like?
There are formulae available for approximate added mass estimation. In fact, it has been recorded in one of our online lectures by Dr. Sohan Suvarna.
Another question I had was, so you did some non-dimensional analysis. There were two axes, I remember. On the when you were meshing, when you were covering that slide on meshing, one of the non-dimensional axes was x by L. The other was y. What? Y plus. Y plus. So is it based on the width of the airship?
So could you just explain what do you mean by y plus values? Because they don't know what is y plus
Okay,
values.
okay. So whenever we do meshing, okay, meshing, especially for subsonic application, the most critical region to be actually refined is the boundary layer. So that if you are able to capture the flow gradients in boundary layer, we will be able to obtain accurate results. So in order to mesh this particular region, there is a particular non-dimensional term that is used in the CFD fraternity that is called the y plus value. This is called the non-dimensional cell wall distance parameter. So what it basically tells is, if you are having a y plus value which is very small in nature, that is y plus less than 5, that means to say that you are able to refine the mesh almost up to the wall of the surface. If you are having a higher value of y plus, then you are able to then your first cell, which is closest to the wall, that will be a little away from the cell. So the lower the value, the more finer is the mesh. So when you refine the mesh too much, there will be a lot of computational cost involved. But when you make use of a higher y plus value, there will be a lot of approximation involved. So based on your computational throughput or computational resources, you can decide your y plus. So in our case, we had made use of y plus less than 1 to understand. So our mesh was the first cell in the mesh was very close to the wall surface.
No, my question was like, how is the value, like, what is the y plus in reference to? If it is non-dimensional, it is divided by what standard value to
So
get the
it is with respect to the first cell height.
Okay, so the first cell height is determined, and according to that, then the
Yes, according to
got it.
that, where you understand the first cell height.
Got
And
it,
that
got
is
it.
also a function of the velocity and the reference length that you're selecting.
Okay, so they are like reduced based on like
Yes.
Yeah, okay, got it. Any other?
Any other questions? Anyone?
So
I
one
think
of
last
your
question I'll have to also have to leave because one
uh,
question I can.
so in one of your programs that you used for CFD, it was OpenFOAM plus Python. Was the
Mhm.
Python just for the data analysis, or was it some programmable CFD?
No, for the CFD part, we made use of the open form. So what we did was I had already developed the required CFD framework to carry out the CFD analysis. Then subsequently, this Python coding was used to develop the active learning framework. So this active learning framework was integrated with my CFD framework to carry out the design optimization.
Okay, all right.
So Python basically acted as a bridge between the two.
Ah, all right. Yeah.
Any other questions, anyone?
Pranav, I think only 1 minute I have to leave now. So
Okay,
one question
so
can
I
be.
think what
So,
we
okay, I
can do.
think Manish,
Mhm.
no, we will thank you. We will thank you officially for
Yeah.
spending such an engaging time.
Okay, sir. It's my pleasure, sir. Always there,
ठीक है,
sir.
ठीक है. Okay.
Okay, sir.
Okay, they
Bye.
also have to take a break now. So thanks a lot. Okay.
Yes, sir.
I'm ending the meeting.
Yes, sir. Okay. Bye, bye, everyone.
Bye bye.